So in the previous video, we talked about how to get this WPILib elevator simulation running, and also how to add a few more outputs to this so that we could display the internal state of the simulation and what's actually going on with the elevator. But today, I want to go back and look at the code in a little bit more detail, specifically this setup portion up here at the top, and the loops down below that actually run everything. So starting with the setup up top, we have a few different types of objects up here that do different things. And I want to separate those and group them so that we can talk about their different roles, because in Java, an object can mean one of many different things. So the first thing that we have up here is this DC motor object, m_elevator gearbox. And this is solidly a simulation object. The purpose of this is to allow us to model the behavior of the DC motors that we connect to the elevator to drive it. So this I'm going to move down to right above our elevator simulation object, because that's another one. So this elevator sim down here is the physics simulation of the real world. You know, if you were to run an elevator in the real world, the physics of the universe is your is what controls how it behaves. But in our simulation, this is what controls how our elevator behaves for a certain set of inputs. So this elevator gearbox object gets passed into the elevator sim constructor. And when you poke values into elevator sim, it pokes values into this elevator gearbox, which is 4775 Pro motors. All right, back up to the top here. This stuff up here, this is all related to actually controlling the elevator. Although I am going to separate this into two groups. The first thing is this stuff up here, this profiled PID controller and this feed forward. These are not really classes for controlling our elevator. That's a little bit it groups too many things. But it's for generating control outputs for our elevator. So right here is the setup. The controller takes in a bunch of constants, takes in that trapezoidal profile. But lower down in the code, as you'll see, we're going to poke two values into the controller. We're going to poke where we eventually want to be and where we are right now. The controller is going to record where we have been over time, and that's why we can do integral and derivative control. And it's going to perform some limiting with this trapezoidal profile. The feed forward is also a calculator. It doesn't care about where we have been. It only cares about what is the velocity of how you want to reach your set point. So it cares about how fast you want to be going, and that's what it takes in, and both of these give you a voltage output that you can do something with. And that brings us sort of to the next part here, which is we have the encoder object, which is how the code knows what the elevator is currently doing. Otherwise, it wouldn't have any view. It would just know, okay, I told it to do this, but that goes out into the ether and nothing comes back. And we have this motor object, a PWM Spark Max, and that is how we actually send a value out. That's how we say, okay, we'd like to control a motor. Where do we put that value to try to control that motor? So I'm going to move these up to the top, because these are possibly the most basic things and probably the most important. So these are our inputs and outputs. We've got an encoder that gives us a look back at what we're doing, and we've got this motor controller, not really motor, but motor controller, that allows us to interact with the world. Then down here, we have this simulation stuff. And that's this elevator gearbox, the elevator sim. And then down here, also simulation related, we have this encoder sim object, which takes a parameter of the encoder up here at the top. And that's because when you're actually running a simulation, this encoder object that you constructed to reference the A channel and the B channel, you know, things connected to the RoboRio, the RoboRio doesn't exist. These digital inputs don't exist. So this encoder wouldn't actually gather any data from the real world. But if you create this encoder sim object, you can then call methods on encoder sim, and it will poke values into this encoder object, so that when your actual elevator control code tries to read the encoder object, it will get something and go, oh, I've got a position. I better control based on that position. And the same thing with this PWM sim object, m_motorsim. It does the reverse. The elevator control code is going to write some value out to, it's going to try to write it out to motor port 0, and that's going to go nowhere because there's no RoboRio, there's no PWM connectors. So this motorsim object allows us to reach in and say, okay, what was the last thing that our code wrote to this motor controller object, so that we can use that and we can feed it into our simulator. And then the last thing down here is we've got this code that constructs the little visualization that doesn't work very well over here. Still doesn't work in 2025. That wasn't updated, apparently. So next I want to go through the loop of what happens every time the robot code runs. So the two methods that are relevant here are simulation periodic and reach goal. And I'll show you how those are relevant. So let's find all references on reach goal. Reach goal, here's the declaration, and then here's the two places that it's called. Both of those places that it's called are in teleop periodic. Then you come back to elevator, simulation periodic, find all references. You'll find that simulation periodic of the elevator is called by simulation periodic of the robot. So if you're curious and you really want to delve into this, what you will find is that when you are in teleop mode, every 20 milliseconds, the robot code calls teleop periodic, and then if you are also in simulation mode, it will, after that returns, and after robot periodic, call simulation periodic. And then it'll wait the remainder of that 20 milliseconds from when it first started the loop, and then it'll come back and call teleop periodic again, it'll call robot periodic again, it'll call simulation periodic, and then it'll go back and wait that remaining time. So that should provide a little bit of insight into why you don't want your code to take more than 20 milliseconds. So come back into here. We're going to start with the reach goal method and just go through and see what happens. So reach goal takes a parameter, double goal, and we know from looking at the robot code that reach goal either is called with a set point of 0.75 or a set point of 0. And the first thing that happens is it takes that goal and it pokes it into the controller. It calls the set goal method on m_controller. And remember, controller is our profiled PID controller. So it's both a PID controller and it also creates and evaluates that trapezoidal profile. So that's the first thing that happens. And there's no output from this. This is just setting that goal and returning. But then the next thing that happens is we call getDistance on our encoder. And getDistance in this case, because the encoder is measuring the height of the elevator, really means what is the current height of the elevator. That value gets used as a parameter to the calculate method of controller. So this says, okay, controller, you have already been told where to go eventually. Now, calculate the output based on what our current location is. So measurement of the process variable, our process variable is the height of the elevator, returns the controller's next output. So based on what our height is and where we're trying to go, which you already know, give us the next output. And this output, by the way, is in voltage. It is a voltage to apply to our motors. And the next thing is, this is a little bit hard to parse because there's a lot of layers of parentheses here. So I'll quickly expand that out so that you can see it a little bit better. If you go to the innermost, remember your math education should tell you to go to the middle of the parentheses first. We say, okay, controller, give us the set point. Set point, remember, is distinct from goal. If you go back to the actual simulation and you look at the set point, this is the goal. This green is the goal. The goal immediately jumps when you press the button. The set point is the orange here. The set point ramps slowly from where we started out to where we want to go. And this is the set point position here in orange, and this is the set point velocity down here on this velocity plot in blue. So the goal, there is no goal velocity because this jumps immediately, right? The velocity would be undefined. It would be infinite. But there is a set point velocity because the set point moves slowly from one position to another. So we're asking, okay, trapezoidal profile, calculate that velocity for us. Tell us where you are along here. So that's what this is. Get set point, and then get set point has a position and a velocity. Give us the velocity of that. And then this is part of the Java units library, UNITS, as in keep track of our units so that we aren't passing around a raw double that is a position in meters and trying to treat it as a velocity in meters per second or something like that. So this call right here, this meters per second dot of, says, okay, create an object that is of type linear velocity unit, and our input to our of is already a double that represents it in meters per second. So that's what's inside of here. And then we're calling the calculate method on feed forward, and the thing that we're passing in is this wrapped up velocity. So when you call calculate on a feed forward object, on this elevator feed forward object, it returns a voltage based on how fast we want the elevator to go. So that's what this means. That's what the feed forward can tell you, is based on how fast you want the elevator to go and in what direction, it's going to give you a voltage output. And it returns that also in, if I can show this here, it returns it in a unit of type voltage. So this object that it's returning is of type voltage, not a double or something like that. So what do you do if you want the raw double? Well, then you call this in.volts, and this unwraps the unit from the units library and says, okay, we just want a double. That double represents voltage. And then, so we've stored both of these in local variables. We've got a voltage from PID output. We've got a voltage from feed forward output. Good. They're the same units. We can add them up. We call set voltage on the motor controller. And this set voltage here, because it's a PWM Spark Max, it says, okay, we're going to, those PWM ports on the Rio, they can't communicate anything other than percent of battery voltage output. So they look at the voltage applied to the Rio and they say, okay, let's say this adds up to 6 volts. This set voltage says, all right, I look at the voltage of the battery right now, it's 12 volts. That means we need 50%. So we're commanding that PWM Spark Max to 50%. Great. Easy enough. So come up here to simulation periodic, because we just finished there. Now we're going to say, okay, motorsim.getSpeed. Now this getSpeed label, this is really terrible, and it's been a problem with WPILib for years at this point. This is not a speed. This does not represent a speed. This represents proportion of duty cycle or proportion of battery voltage. So this would come out, in our 6-volt example, this would come out as 0.5 because we want half the possible battery voltage applied. And, all right, we're looking for set input. We're looking for the voltage that's going to be applied to the motors. So we have to call robotcontroller.getBatteryVoltage to give us the battery voltage, to multiply by 0.5 to get us back our 6 volts here. And the reason why this is important is because this set voltage, again, it strips out the actual voltage. That's why we can't pass a voltage directly back up to here. Whenever you're using a PWM port, there is no voltage conveyed. It is just a proportion of max voltage. So anyway, we take that, we create this voltage again, and we poke it as the input to our elevator sim. We're saying, all right, those motors in your elevator sim, we are applying 6 volts to them. Cool. Next, we update it. The loop time is 20 milliseconds. Good comment. So we're saying, run the elevator sim for 20 milliseconds, having just applied this voltage to it. What happens? So we've advanced the simulation. Then we come in here and we pull out the position of the elevator, the height of the elevator. So we say, elevator sim, you ran for 20 milliseconds at 6 volts. What happened? And we take that and we poke it into our encoder sim. So we say, okay, whatever the elevator sim says the height of the elevator is, that's what the encoder should read. It makes sense. This is what the elevator would do in the real world. You would apply some voltage to the motors, you would wait some time, and then after that time, the output would appear as a change in the encoder reading. And then finally, the other thing that happens, the side effect, so to speak, is when you draw current from the robot battery, the voltage is going to change. So we want to ask the motors, okay, when you did this, when you applied 6 volts, maybe the elevator was stationary, and so we're going to draw a bunch of current, just like a robot accelerating from a standstill. You see the battery voltage drop when that happens. So figure out what that current draw was, and then on this battery sim object that I know we're pulling out of nowhere, it's always available in simulation, calculate what the battery voltage would actually be. So we started out at 12 volts because we were doing nothing, and let's say, now we calculated this and it's like, it's 11 volts because we're pulling a whole bunch of current. We're going to poke that value into the RoboRio sim, and that eventually will come back out up here. So I know it's a little bit confusing that these two are different, but you can poke a battery voltage into RoboRio sim and get it back out of Robot Controller. But anyway, that's what happens in simulation. Again, this part is intended to simulate what the robot would actually do if you were running it in the real world. So now, this took however long, we're going to wait until the beginning of the next 20 milliseconds, and we're going to come back to reach goal again. So, whatever that goal happens to be, we're once again going to poke it into the PID controller. We are once again going to ask, what is the position of the elevator? And remember, this position of the elevator, now it's no longer just, whatever startup position is. It came from set distance up here. So that came from our simulation. So there's our loop back. And we're going to poke that into the controller, ask it to calculate, okay, what do we do? And we're going to do the same thing. We're going to go, okay, controller, based on what's going on, give us our velocity set point so we can calculate our feed forward output, and then come back, add these up, poke that into the motor controller. So, okay, now we've poked that value into the motor controller. We come back up here. We get that value out of the motor controller. We look at the voltage. We poke that into our elevator simulation. We run the elevator sim for 20 milliseconds. We take the output of the elevator simulation. We poke that back into the encoder. We update the battery. And then we wait again, and we do the same thing all over again. And that is what gives us the result that you see here. So this is running. This is saying, okay, I'm always poking that position I'm also poking that goal position from reach goal, and I can vary that position by clicking my simulated button 1 on the joystick. And this is how it responds. This is what the trapezoidal profile is doing. It's calculating this position over time, and the simulation is, along with this little noise in here, is following along. It's behaving like an elevator should.